Welcome back, and in our previous video we set up the concept of integration with a word problem where we were modeling Sam riding his bike at a certain velocity, and we found out the distance traveled by looking at the area under a curve. Now we're going to look at a general 5.1 numeric integration techniques, and in general, and we'll set this up in general and then work a couple homework problems. Here's these acronyms that we'll define. The LRAM is the left rectangular approximation method. Okay. The RRAM will be the right rectangular approximation method. The MRAM will be the middle point rectangular approximation method, and then of course we'll get the trapezoidal method. But what we're really doing is the same thing we did in the last video, is we are trying to find, say from A to B, we are estimating what the area is under this curve by adding up the area of rectangles. Okay, we're trying to find this area underneath here. Okay, that's what we're trying to do. And then the next slide will define what these different methods are to do that. And then what we're going to do, eventually we're going to get an exact answer, and the exact area will be this integral, what we call the integral. Okay, back to our study of integration, and we're looking at this function f of x. We're looking at the function f of x, and we're trying to approximate the area under the curve. And notice we got these various x values, a, x2, x3, x4, and b. Our interval's going from a to b. We know the heights here. This is what's the height of the curve? That's f of a. This height here is f of x2. The height of the curve here is f of x3. The height of the curve there is f of x4. And you might guess the height of the function at b is f of b. That's what that function means. Now let's talk about the first way to do it. Now notice these aren't perfect rectangles. We got to approximate the rectangle somehow. And the key is going to be, well, what are you going to use for the height? If we use the left-handed rectangular approximation, we're going to, as you might guess, we're going to use the left-handed height. Okay? We're going to use that height there. And we're going to use this height here. And we're going to use that height here. And that height here. So these will be our rectangles. I don't know how messy this picture is going to get. We'll give it a go, though. Okay, so there's our rectangles. Notice there's error here. You see the error right there? That's not really under the curve. This isn't really under the curve. If we were going to do it, though, we'd say this is, well, first of all, we also have to come up with what is the width of these. What is the width of the rectangle? I'm going to call the width of the rectangle delta x, and I'm going to say the width of the rectangle is uniform, so all these widths are delta x. They might not be, they don't have to be, but we'll say we have uniform widths. So if I use the left-handed rectangular approximation method, the area of my rectangles is going to be what? Well, it's going to be, the first one is going to be f of a times delta x plus f of b, f of x2 times delta x plus f of x3, right? What's the height of this first rectangle right here? It's the height f of a times the width. And I'm adding up what? 1, 2, 3, 4 rectangles. Okay, so my left-handed rectangular approximation method, notice I'm adding up one rectangle, 2, 3, 4. I could write this as the following. I take the left-handed heights I multiply those all by delta x. This assumes that delta x is uniform. All these rectangles have the same width. Okay, well, what do you think about the, notice I happen to pick the left side. The left side, oops, the left side has some errors. As I said, there's an error here, here's an error here. I got a little bit less than I needed here, and I'm missing that. So it's not a perfect approximation. I could try the right side. Well, if I go to the right side, that means I use the right side of the rectangle as the height. And here's my height here. I get that one. I go up the right side, I get this one. I go up the right side here, and I get that one. And then I get this one. So now my areas look like this. My areas now are in blue. And you see they introduce their own errors. Both the left-handed and the right-handed have their problems. But if you did this again, I'll skip the first step of this, and you see here is, for my right-handed method, I use the right-handed heights, the right side heights of the rectangles. All times delta x. Okay. If you wanted to use a trapezoid, here, a trapezoidal method would be, because the left, you can see there's error in the left side, that's what's missing or added from the red rectangles. There's error in the blue side. Here's missing, I'm missing area here, I'm missing area here, I'm adding area, and I'm adding way too much here. A trapezoidal is, now they're not rectangles anymore, you're actually doing this. You're making a trapezoid, and now you've got not rectangles, but trapezoids. So you're going to go like that. And as you might guess, a trapezoid is the average. The trapezoid is the average of this height, right? This is L1, and that's L2. A trapezoid, the area of a trapezoid is the average of this height and this height times the width here, the width of the trapezoid. So you can look that up, and if you go through adding up a bunch of trapezoids here, all the way down to this one here, if you add up 4 trapezoids, you'll find out this is exactly equal to the answer you got when you took the left rectangular method plus the answer you got with the right rectangular method, all divided by 2, which is nice. It gives you an average of 2. It's going to give you an average of 2 processes, so it's probably going to give you a better answer. But we introduce these rectangular methods just so you can get an idea. What is an integral? Well, it's the area under the curve. What does it mean? Well, I gave you the word problem with Sam on his bike. Now for this section, let's just work a typical problem where we're going to calculate the area under the curve. Okay, here's an example problem where we're going to use rectangular approximation methods in order to estimate what the area under this f of x looks like. And what they first they want us to have 6 rectangles. Okay, 6 rectangles. Notice I'm going from, this goes up to 12. So each rectangle, my delta x is going to be equal to 2. Let's try this with, we'll keep our same color code here maybe. Let's start with LRAM. If we do the LRAM, we're going to have what? Well, we're going to have this, and then this. And this is going to get a little ugly, isn't it? Okay, those are going to be our our rectangles here. Okay, and we're going to add up what? 1, 2, 3, 4, 5, 6 rectangles. What are they going to be? Well, it's going to be the width of each one's going to be 2. Then I got to estimate the height. It looks like it's 9. Plus this one here is, let's see, 9. Shoot, I don't know, 9.6. No, sorry, 8.6. At this point here, I'd say it's 8.2. Okay, 1, 2, 3, 8.2. This one down here, that height right there is what, 7.2? 7.2, that one, that's a nice one to estimate. That's right at 6. And this one, that's pretty easy. That's plus 4. Okay, so it's 1, 2, 3, 4, 5, 6. Okay, we'll come back after and get a calculator on that one. Let's change our color code though, and let's go to right rectangular. And if you do these long enough, you'll say, well, that's 2. And you're going to use all these. You're going to start with, now you're going to have this height here, this height here, this height that way. You're going to go on the right side. Okay, that side. But now you've got this little rectangle here. Okay, so you're going to have these, this, and this. And what you find out is you bring all these heights down. You bring all these heights over, and then you add 1. You add this particular height, which looks like 1. So you get 4, 6, 7.2, 8.2, 8.6. You might think, are we going to do this all the time? Is this what integration is going to be like? No. When we start off doing this, so you get the idea about area under the curve. That's what these rectangles are. Okay, so we're at 12 minutes here. If they also asked about the midpoint, which I didn't talk about before, but I bet you could figure that out. I bet you with a little bit of thought, you could say, well, I'm now going to use the midpoint of each one of these triangles. Now, of course, all my heights change, so it's not quite, if I want to use the midpoint, oh, better go to black, let's go to a different. The midpoint would be that height. And this height would be the midpoint of every, I get that right, yeah. So this is my height here. I'm using the midpoint as the height of my rectangle. Okay, now I have these triangles. Can you see? I don't know, that probably didn't help. Okay, so the midpoint is now going to be 2 times, I got to figure out what's that point at. Ooh, that's almost at 9. We'll say 8.9. This point here is at 8.5. This point here really looks like it's at 8. And so on. Okay, I did the computation a little bit offline here, and you see I calculated that when I used the left end points, I got 86. The right rectangular method, I got 70. And you can see from the left one, look at the left is in, the right one is in red, and look at all the extra space. That looks like an overestimate. And if you, I've since erased the other one, but the right rectangular was an under, this was an over, this was over. This was like an underestimate. And so if you wanted to know, the most accurate one was the midpoint. That was the best one for this particular function. Depending on the concavity of the function, you'll see different methods will work better. Okay, so that's, again, we're area under the curve. We're using rectangles to approximate the area. You might wonder, how can you make this more accurate? We use 6 rectangles, right? What if we use 12 rectangles? Yes. Of course, if you use 12 rectangles, you'd get more accuracy, but you'd have to work a lot harder. So we'll see how we handle that as we go forward. See you soon.